Okay, so you've stared at a definite integral, right? You know it's supposed to be the area under a curve, but actually finding that area can feel, well, super abstract and complicated. Today, we're going to blow right through all that complexity with a powerful shortcut that will totally change how you look at these problems. You might remember the old school theoretical way of doing this. Slicing the area into an infinite number of super duper thin rectangles and then adding them all up. It's called a Riemann sum. It's a cool idea, I guess, but trying to actually do it, yeah, it's a complete nightmare. But here's the good news. We almost never have to do that. Thank goodness, right? There is a much, much better way. It's direct, it's elegant, and it's a total game changer in calculus. We're calling it the subtraction shortcut, and it is going to make your life a whole lot easier.
Okay, let's dive in. So, the fancy name for our shortcut is the Fundamental Theorem of Calculus Part 2. And what makes it so fundamental? Well, it's the rule that forges this incredible link between an integral and its exact opposite, the antiderivative.
And here it is, in all its glory. The integral of a function from some starting point A to an ending point B is just its antiderivative. That's the capital F, plugging in the endpoint B and then subtracting the antiderivative with the start point A plugged in. That's it. No more infinite rectangles, just one clean subtraction. And here's a way to think about it that makes so much sense. If an integral is all about adding things up, like total accumulation, then this formula is just saying the total change is simply the final amount minus the starting amount. Think of it like end height minus start height. It's a super intuitive idea when you put it that way. Okay, enough theory. Let's get our hands dirty and put this theorem to work with a classic polynomial. We're going to find the area under the line 2x plus 1, starting at x equals 1 and stopping at x equals 3.
First things first, step 1 is always to find the antiderivative. So we just do the power rule in reverse. The antiderivative of 2x becomes x squared, and the antiderivative of 1 is just x. So our capital F of x is x squared plus x. Easy enough.
All right, step 2. We plug in our numbers. We take our antiderivative and pop in the top number, which is 3. That gives us 3 squared plus 3, which is 12. Then we do the exact same thing for the bottom number, 1. That's 1 squared plus 1, which is 2. And now for the best part, the final super satisfying step. We just subtract the bottom from the top. F of b minus f of a. In our case, that's just 12 minus 2. And boom, the answer is 10. The exact area under that line from 1 to 3 is 10. See? Simple, clean, and honestly, pretty powerful stuff.
All right, you ready to level up? Let's see how our shortcut handles something a little trickier, like a trig function. We're going to find the area under one whole arch of the sine wave, from 0 all the way to pi.
Okay, step 1, find the antiderivative. And listen up, because here's a spot where a ton of people mess up. The antiderivative of sine of x is times negative cosine of x. It's so easy to forget that little negative sign, but it changes everything.
Now we evaluate and subtract. So we've got negative cosine of pi minus negative cosine of 0. And look, I'm using parentheses here to keep all these negative signs from getting tangled up. Trust me, it's a lifesaver.
This is exactly where those parentheses pay off. Okay, let's break it down. Cosine of pi is negative 1. So negative cosine of pi is positive 1. Then cosine of 0 is 1. So negative cosine of 0 is negative 1. Our whole problem becomes 1 minus negative 1. You got to watch those double negatives. And of course, 1 minus negative 1 is just 1 plus 1, which gives us our final answer, 2. The area under that entire arch of the sine wave is exactly 2. Pretty neat, huh? All right, time for our final challenge problem. Absolute value functions are kind of special because they have that sharp corner, that v-point. And calculus doesn't really like sharp corners. It means we can't just find one simple antiderivative for the whole thing. So we need to add an extra step to our plan. So here's the secret. We just split the integral right at that v-point. For absolute value of x, that point is right at x equals 0. You see, on the left side, from negative 1 to 0, the function just acts like the line negative x. On the right side, from 0 to 2, it acts like the line positive x. So we just turn one tricky problem into two way easier ones. Now, all we have to do is solve each of these little integrals separately using our shortcut. As you can see here, that first chunk, from negative 1 to 0, works out to 0.5. And the second chunk, from 0 to 2, comes out to 2.0. So, since we split the area up into two pieces to solve it, what do you think the last step is? You got it. We just add those two answers back together. We take the 0.5 from the first part and add the 2 from the second part.
And there you have it. Our total area is 2.5. By just splitting the problem at its tricky spot, we made what looked like a really tough integral totally manageable.
Phew, we've covered a lot. But the really amazing thing is that no matter how weird the function looks, the process, the recipe, is always the same. So let's just boil this all down into the core method you can use every single time. It always comes down to these 3 simple steps. 1. Find the antiderivative, your capital F of x. 2. Evaluate it at your top number, f of b, and your bottom number, f of a. And 3. Subtract. Top minus bottom. Anti-differentiate, evaluate, subtract. That's the shortcut. That's the whole game.
So now you have this amazing tool. You know how to find the total accumulation of, well, anything. And this is so much bigger than finding the area in a math problem. This is how you calculate total profit over a year, or the total distance a car has traveled, or the total amount of water that flows through a dam. So the real question isn't just what you can calculate. The real question is, what will you measure?